Good morning, everybody. This is Brandon Burton with Restoration Sciences Academy and Legend Brands. I thank you for joining me today for this fifth installment in our series of webinars. And today we're going to focus in on reviewing some of the content that we had in the first 4 parts of the series. As we went through the first 4 areas in the webinar, we discussed some of the intermediate information related specifically to controlling a drying environment, then monitoring those conditions to ensure the best level of efficiency in the drying process. And today, we're going to go through the most pertinent content from those first 4 webinars and tie them together into some conclusions, which will conclude the intermediate part of our webinar series. Then beginning next month, we'll start going into some of the more advanced topics in restoration and really keying in on the mechanisms we use to solve drying challenges and drying problems and expedite the speed of drying. So I thank you for joining us today. Just a quick reminder, we have some information on screen. If you have some technical difficulties as we go through the process, feel free to use the chat icon in the upper left-hand corner or call directly into our UK office and ask for Ann or Colin. So again, thank you for joining us. So let's go ahead and get started because we have a lot to cover today. First and foremost, the first module that we discussed several months ago was the importance of airflow. And the reason why we began with this module is because by far the most impactful way that we can affect the speed of drying is to manage the transportation system in drying, and that is air movement. Several concepts that we discussed in this process, but the conclusion of those concepts is basically that air movement provides the ability for the qualities of air, the temperature and the humidity of air that affect drying, to be properly placed into contact where the surfaces are where drying is occurring. And without the appropriate transportation, it really is irrelevant to have those conditions present. If you have a great temperature and a great humidity in the center of the room or the core of the room, that does not in any way, shape, or form translate to drying at the surface. Unless the two contact one another, they must come into contact with one another. And that's what air movement really provides. It allows the temperature and humidity to be evenly placed into contact with surfaces where drying is occurring. There are several studies that have been produced on this that have all types of values for the speed of the air movement that is important, but all of those studies agree that air movement is a multiplier of the drying process. We'll take a look at a formula for that here in just a moment. And that drying rates are dramatically impacted when appropriate airflow is supplied. On screen right now what we see is a typical drying rate. They call this a absorption isotherm if you wanted to get technical, that shows the rate of drying of a given material without airflow being placed across the material. And the drying rate's relatively slow and constant as we move through the drying curve. And this would be the same as if we were talking about the state of change in matter for really any energy change process. And the example being given in this particular slide is the rate of change of a solid ice to a liquid water. This is the same type of change of state that we see in drying, where we're trying to take absorbed or liquid water and make it a vapor. So in other words, ice moving to liquid and liquid moving to vapor is pretty much the same physical process. And if you'll remember from the analogy that we had in the first module, we gave an example, and that example was if you took an ice cube and placed that ice cube into a glass or a bowl of water and poured regular temperature tap water into that container, the ice cube would melt eventually. And as that ice cube began to melt, the rate of melting would actually begin to slow down. And the reason for that is because the ice would make very cold water around it as it began to melt. And that cold water would slow down the process, slow down the energy transfer. But we could speed that process if we began to stir the water. By moving the water around in the container, we could cause the rate of melting to increase. And that gives us an example of how important that transportation is, the airflow is in a drying process. And it's a great way to prove this out to yourself. If you haven't done that before or haven't done it since our first module, I highly encourage that you do it. Just take an ice cube, place it into a container of water, and begin stirring that water. And watch how rapidly the ice melts. You can actually time it. And then repeat the process without stirring the water. and time how long it takes the ice to melt. And you're going to see an order of magnitude in difference in time. That order of magnitude would look something like this. You'd notice that the rate of drying would be half or less. The rate of melting would be half or less with transportation versus without. This directly translates into your ability to dry structures rapidly. If we sufficiently provide airflow, we're going to notice a substantial reduction in the overall amount of drying time. Now, understanding that reduction in airflow increase in airflow to reduce drying time requires again that we remember two very important principles. Important principle number one: air must be in direct contact with a wet evaporating surface. And in this analogy, the airflow is several centimeters above the floor. That air movement is going to have zero impact on the ability to dry that floor. In order for that air to have impact, it must be in direct contact. That's the only way that it's going to have an impact. So it's important that we evaluate that as we install air movement, not only by location and where we place it, but also the type of air movement that we use. Using traditional box fan type or paddle fan type air movement does not place airflow into contact with surfaces, and that's part of the reason why we have very specific technologies available to us in the industry today. And taking a look at some of those technologies, here is an example in thermal imaging of an analysis that we've done here at Restoration Sciences Academy on different air moving technologies. And what you're looking at in the thermal imaging are areas of rates of drying, if you will, and the red to white areas represent a location where drying has been very successful because of an air mover that has been placed at the very top of the image. So air mover is placed in this location, and it's blowing air out across this surface that has been wetted. The areas that are blue to green are areas where there is not a lot of successful drying. And without getting into thermal imaging in any depth, just use that as a general indication of what we're looking at. As you look at different air moving technologies, one thing that you'll note is that different types of air movers have very different impacts on the drying effort. And the reason for the difference is the amount of air that the air mover places into direct contact with the surface. And what's interesting is that it doesn't really matter what the CFM or cubic meter per minute of airflow is coming out of a particular device. The volume of air coming out of the air mover is generally irrelevant. What's more important is the speed of that air, the velocity of that air, and the direction of that air. Is it organized and directed at the surface? For example, the air mover that is giving us the best performance in this analogy, the one on the very far right-hand side, actually has a substantially lower volume than the air mover in the center. And the air mover on the very far left-hand side actually has a better velocity than the air mover that is on the far right-hand side. But all of that said, those specifications are irrelevant because the work that is actually being done is being done by the directed air movement at the surface. We'll come back to that in a little bit later in the discussion here. So point number one is we have to have the right technology directing the air at the surface. Point number two is we then have to place those air movers to ensure that we are giving every wet surface an equal opportunity to dry. And there's a very strategic way in which we make that happen. First of all, it's important that we're using a couple of different technologies. First, you need a technology that is going to allow you to move air between spaces efficiently. And there are a couple of air mover types that do that. The one that I'm going to pull out as an example here is going to be the centrifugal type. If you're looking at the Legend Brands product line, that would be something like a Sahara. The other type that's important is then distribution over a large open area, which is typically best done with some form of an industrial axial that's been designed for surface airflow, and we'll take a look at that here in just a moment. This general strategy is that we want to follow the wall assemblies and utilize those assemblies much like the ductwork that would be available from a heating, ventilating, or air conditioning system in a structure, ensuring air is mixing from one room to the next. This is the first part of transportation, because if all of these rooms have moisture, I need to verify or ensure that all of these rooms are receiving the warm, dry air being created by my dehumidification systems. And without this mode of circulation, you're going to end up with some rooms that are warmer, some that are cooler, some that are more humid, some that are less humid, and the building's going to dry at different rates. And regardless of how quickly you dry one room, you can have one room dry in a week. If it takes you 3 weeks to dry a different room, then the job took 3 weeks. So you're only as good as the slowest area of drying. So ensuring this good, even circulation helps mitigate those areas of slower drying that make the overall project take longer. Now, getting that direction of flow, we're going to use this centrifugal air mover, and we're going to place it strategically at the openings of these doorways. Notice how when we place these air movers in these locations, the air mover has a specific intake, which is over here on the far right-hand side of the air mover, and a specific outlet. Over here on the left-hand side of that air mover, this is not an inlet. It's the end of the motor. It's a power switch, maybe some sort of electrical circuitry there. And every air mover, the centrifugal type manufactured in the restoration industry across the globe, is going to be designed in exactly the same way. That intake is always going to be on that left-hand side, and the outlet's always going to be in the front. So designed in this fashion, notice how these air movers will always draw the air from the neighboring room, then force that air around the perimeter of the entering room. This ensures and forces appropriate circulation between spaces. Now, to validate this, it's critical that we then take a thermal hygrometer and take measurements in each of these rooms to ensure that the temperature and humidities are constant between these spaces. If there is any substantial deviation in temperature and humidity, there will be a substantial deviation in drying rates, which is going to be problematic because where you don't have the same temperature and or a higher humidity, you're going to get slower drying. And again, regardless of how quickly you dry one room, the job took as long as the longest room or the longest area or the longest space. So that's the first layer of installation, room-to-room circulation. Once the room-to-room circulation has been addressed, then we need the field of the floor. And the field of the floor must have an ample, sensible rate of airflow across every single point on that floor in order to continue to support the rate of drying, much like the ice cube analogy that we started with. This is generally best addressed by using an industrial axial type air mover, but not your standard axial that's used to duct air out of a building or into a building. One that would have a duct ring on it, but one that is designed with legs and features that allow you to place it in a downward flow towards the center of the room. Now, there are two major reasons why this will be needed in the middle of the room. If you'll notice on my slide, I have one room that does not have this air mover installed, and I have two rooms that do. Two primary reasons for it. Number one, if you're in a space that has a lot of contents, and those contents have been moved out away from the wall so that we can get access to those walls, then in the center of the room, those contents are going to create restriction, and you're not going to get ample flow out in the middle of the room. The second reason why it would be needed would be because of the size of the room. Once we get airflow moving around the perimeter of the room in a smaller space, generally that's going to cause airflow over the entire surface area within the room. And in a larger room it won't, just because of the general size of the space. We validate this by walking out into the middle of the room, and you grab a hygrometer, believe it or not, and with a thermal hygrometer you measure the temperature and humidity about 3 or 4 feet up from the floor, about 1 meter up from the floor, and then you take that same hygrometer and place it directly in contact with the surface. And if I can get the same humidity at 1 meter above the floor as I'm getting right at the surface, then there's enough airflow. However, if I see a substantial deviation in the temperature and humidity 1 meter above the floor versus right at the floor surface, air is not moving fast enough to bring that moist air away from the surface and replace it with the drier air in the balance of the room. That's a critical measurement, and you should be able, if you've installed air movement appropriately in enough quantity, you should be able to see the same temperature and humidity anywhere within that drying space that you place a thermal hygrometer, because that's what air movement's there to do. It's there to mix that air, distribute that air, and ensure the wet surfaces are getting the same temperature and humidity, the same opportunity that the center of the room is yielding. Once you've established this, then the other question that often comes up is, how do you install or place dehumidification? And in reality, it doesn't matter. A dehumidification system could go anywhere in this example on this slide, as long as I've got good airflow across the surfaces, good airflow from room to room, it is irrelevant where the dehumidifier goes. So as a general summary on the air movement side, air movement is the most impactful component of our drying equipment for ensuring that we're going to get a rapid drying rate. As a consequence of appropriately installed air movement, we then need to consider in Module 2 how to balance humidity and temperature control with that air movement. We generally discuss this model as something called HAT, humidity, airflow, and temperature, sometimes referred to as the drying pie. But these are the three characteristics in total that manage the ability to dry within a space. And all three are critical to the drying product, if you will. We generally represent this in a model that looks something like a pie. And the reason why we do is because it communicates how important it is that we have a balance of all three. It would not matter which of the three is missing. If one of them is indeed missing, then we will not have a successful drying process. And I'll just give you a quick case in point. If I had tremendous amounts of airflow covering every surface within the structure I'm drying, if I had a very warm and appropriate temperature, but the humidity in the space was at 90 or 95% relative humidity, we don't have a drying environment. We have a rapidly damaging environment. My air movement at that point is circulating highly humid air, and as opposed to causing drying with that air, it's going to cause wetting and secondary damage. So just as a quick case in point, it doesn't matter which of these three components is lacking. If any of them are indeed lacking, then we're going to end up with problems in the drying process. So taking a look at that and drilling in a bit deeper and looking at it in a formulary expression without actually going through all the mathematics behind this formula, here's the very, very simple. When you look at evaporation and you look at the peer-reviewed and time-tested calculations for evaporation rates, they're all going to have the same basic component to them. And that component is that velocity of air, the temperature of the water we're trying to evaporate, and the humidity in the air touching that water. Those are the three components that determine your evaporation rate. You can literally calculate it on a calculator and determine how many liters per hour are going to evaporate from any given surface if you can define and quantify these. Now, we don't need to do that. That would be a little more work than we need to do in our average monitoring visit. But we learned something very important from this calculation or from this formula, and that is that the factor for velocity is a multiplier of the overall evaporation rate. Meaning the faster air moves, the greater the evaporation rate will be, as long as that air movement is along the surface of the wet area. If you'll notice there, we've got the symbol of A, the surface area of water, and that's an indication also in the calculation that this air movement is directly on that surface. So greater velocity, warmer water, and a lower humidity air equal the fastest drying rate. The other note that I'll make on this that's important, because it's going to draw us into another discussion we'll have here in a moment, it's that not the temperature of the air that drives the drying process. The temperature of the air only assists the drying process secondarily because it has an influence on the temperature of the water. It's the temperature of the water itself that influences the drying process. So if we were to summarize all this, move air really fast over warm water and keep the humidity low, and you'll have a great evaporation rate. Pretty simple and straightforward, but it's very important to pay attention to the small words in the sentence. With that in mind, balancing humidity, airflow, and temperature over time through the drying process, we see some changes in the priorities between the three. The calculation that we just looked at showed us that airflow was a multiplier in terms of the drying rate if the air was in direct contact with the water. Now the problem is that as we begin to dry buildings, it's easy to get air right on the water initially. However, once the surfaces begin to dry and the water is inside of the pores, cavities, holes, openings, and voids within the structure, the assembly, and the material, it becomes impossible to have air actually come into direct contact with the water, because now we're drying water that's trapped inside the material. And because of that, as we move out of the relatively easy phase of drying and move to drying materials internally, the impact and therefore the importance of air movement begins to diminish. And what becomes more important is having an even lower humidity at the surface, almost like a vacuum, a low vapor pressure to draw moisture out of the materials, and a warmer temperature in the material itself, which actually generates a vapor pressure, increases the force driving moisture out of materials. As we move deeper into the drying process, that becomes even more extreme. So we begin with an emphasis, a focus on high rates of airflow and humidity control. We then move to a focus on problem areas with slower drying, something we're going to expand on tremendously next month in our next webinar. We begin to focus more on ensuring we have the right amount of energy in the areas that are not responding appropriately or drying slowly. This balance of gauging temperature and humidity and airflow has a significant impact on the net result in our drying time. If we were to take a look at a drying rate where we were just naturally relying on a dehumidifier in the room without an appropriate amount of airflow, again, the overall drying rate is going to be extremely slow. If we have appropriate airflow in the beginning stages of the job, we have an impact that will reduce the overall drying time by more than half. However, that's only going to get us part way to our goal. Now we've gotten rid of the easy water, which is important. Now we have to tackle the water inside of building materials. If we progress again without making any adjustment or focus on the necessary components of humidity, airflow, and temperature, the drying rate again is going to be relatively slow. Now, if we started with good airflow, it's still going to be better than if we hadn't, but it's still going to be slower than it could be if we're leveraging humidity, airflow, and temperature appropriately. Properly leveraging the energy available on the project, however, is going to give us that overall best drying rate. Now, this particular slide and this discussion on managing energy is going to be the key component of our next module as soon as we start getting into the more advanced topics. We'll touch on it a bit more in the summary slide on today's presentation, but it's going to be the core of our discussion next month. The next module we discussed was monitoring efficiently. It's important once we install the systems for humidity, airflow, and temperature control to realize that every job is highly unique, every building is unique, every occupant is unique, and the circumstances of each job or project, therefore, are going to vary. I have a particularly unique kind of perspective on this. I have a facility that I have personally flooded and dried for training purposes more than 300 times, the same exact facility. And I often say that, by now you would think I would know exactly how that building's going to dry every time I get it wet. And what's interesting to me is that I'm reminded every time that I flood and dry that building that every job is highly unique because it never dries the same twice. There's always something different about the way that it dries. And there are several reasons for that. Some of the reasons are because the weather is always a little bit different, influencing the drying process. Some of that is because I have different occupants, if you will, or other people influencing the space. The building materials are never the same after they've been wetted and dried, so there's always variables related to that. In other words, you can never 100% be certain that any installation of any equipment is going to work against any assembly. We make a good, educated guess, what we call a hypothesis, and then we have to come back and verify that that hypothesis was accurate. I personally find that about 80% of the time, as long as we did a good inspection initially and we followed the principles that we just discussed, that 80% of the time it's going to be effective and 20% of the time it isn't, and that's fine. I don't mind being wrong 20% of the time. The major issue is that I don't like to be wrong for very long, because the longer I am wrong in that environment, the more deeply the water absorbs, the longer that water remains stagnant, the more damages the water causes, the more microbial growth becomes a concern. In other words, it's all right to be wrong, as long as we catch it quickly. And that's where monitoring comes into play. Monitoring needs to be extremely timely. It needs to be done in a reliable, repeatable format. But at the same time, it has to be done very efficiently because it's something that requires labor and resources, something that requires energy and time in terms of just not only collecting the data, but considering it and understanding what it means to the drying process. So we spent in our more recent module some time discussing this. And the analogy that I gave is that it does not matter how efficiently we do anything. how efficiently you move air, how efficiently you generate heat, how efficiently you control humidity, or even for this poor soul, how efficiently he's digging his hole to get out of his jail cell. If we don't step back and monitor what we're doing, then that efficiency can be disastrous. All right, knowing where you're headed, in other words, is pretty important when you set out on your goal. And in terms of a drying process, our goal or our role as restoration contractors, as drying contractors, is to create this environment where we're literally putting Mother Nature on steroids. We're exciting the thermodynamic and physical processes behind matter-changing state. Done right, it's a wonderful thing. Done wrong, it can be highly disastrous. Because once you add a bunch of energy and air movement into a building that has a whole bunch of water, it's either going to turn into a dry building or a petri dish in very short order. It all depends on how effectively we're controlling the resultant humidity in the space. So very important that we do that monitoring so that we understand the impact that we're having on the drying environment. Now, to get into understanding monitoring and the process behind monitoring, this is what we call the problem-solving process for restoration, this flowchart. We spent a little bit of time discussing it over the last couple of webinars, the last couple of months. Very brief overview here. There are two stages, primary stages in this process. One of those stages is what we refer to as inspection. It's the entire top half of the chart, knowing what is wet in the environment. And then once we make that determination for what is and isn't wet, determining what should be restored versus replaced. Replaced being the RIP analogy, restored being the HAT, humidity, airflow, and temperature analogy. Making that decision based on a triage. A triage meaning we look at contamination, damage, cost of the item of drying, and understand what is most feasible in order to bring the building back to an occupiable condition. Once we know what we're going to restore, then we continue the inspection and determine exactly how wet those building materials are. That begins the drying process. Then in the middle of the chart, we'll talk about that in a moment, we monitor that. Then we come back in and finally inspect to determine that it's done, that we've achieved appropriate moisture levels in all of the building materials that we were drying. Now in the middle of that, for the entire interim period of drying, we focus on monitoring and the most important component of the process. Trying to realize, is the building making forward progress? Are we moving in the right direction? In this process, we have to measure the materials with the same meter type, on the same setting, at the same location, on the same assembly, and determine whether or not the numbers, the values we're getting from those instruments are decreasing. Very important, by the way, that we follow that exact process. If we use a different meter, we're going to get a different number. If you use a different setting on that meter, you're going to get a different number. If you put it at a different location on the wall, you're going to get a different number. And therefore, inconsistency in that process is going to lead us to inaccurate conclusions about whether or not we're making progress, which is a tremendous risk, liability, challenge, etc. We must know if we're making progress in order for us to decide as the professional contractor that we're moving in the right direction. If I can't make that decision conclusively, then I'm going to make the wrong decision about my next steps. Now, if we're not making progress and we're not moving in the right direction, then we have to go all the way back to square one and reassess what we're doing. What you're doing isn't working, right? It has to change. If you're familiar with the medical condition of insanity, insanity is when he or she does the same thing over and over and miraculously expects something different to occur every time. That's the clinical definition of insanity. So the restorer who goes out to a project and follows up with a monitoring visit and realizes that the wall isn't drying, but then does not adjust the system he's using to attempt drying, is clinically insane. And I'm always surprised by the amount of insanity we have in our industry. An adjustment there is absolutely critical. It must be made. Again, a future webinar discussion will be those adjustments and how we make those adjustments. Moving down the list here, however, if it is drying, if it is making progress, wonderful. All right, then we ask that final question, is it done? Moving away from the general discussion on monitoring and into what monitoring can look like in terms of documentation. There are many different methods by which we can record the information from a monitoring process. But here's a good example of what good monitoring might look like. The first thing I would draw your attention to is to the right-hand side of this monitoring sheet. And if all I told you is that down is good and blue is the goal, then pretty instantly you'll be able to look at this documentation and say, hey, we did good and we met goal. The major purpose in documentation, first degree of purpose, because there's two major purposes. The first degree of purpose is for you as the restorer and your technicians to rapidly identify that we are indeed making progress. Right, and you do that by taking a look at the numbers on the left-hand side and tracking these numbers decreasing by location. And where they are not decreasing by location, we make adjustments. But the second degree of purpose for documentation is for you then to submit this documentation to the other parties you're working with, whether it's the insurer, the property owner, or some other agent or party thereof. And when I supply this documentation to that individual, I want them to look at this documentation without question, without thought, without conversation. I want them to see that the documentation absolutely supports the fact that we have rapid rates of progress. All right, and those rapid rates of progress that we're seeing in our documentation, as noted here within this slide, those rapid rates of progress should be visual. All right. I apologize here, I'm having some issues with the computer. But with that noted, this documentation is a great example of what we're looking for in terms of that communication. Now moving forward, the final module that we got into in our discussion was then optimizing those drying conditions. And in optimizing the drying conditions, we zeroed in and focused specifically on sizing our drying equipment to match the project. In the process, or in the flow chart that we looked at just a moment ago, the table that I very quickly glanced over is the chart that helps us show or demonstrate the way we size dehumidification to a project. And there are a number of methods out there in industry for sizing dehumidification to a drying project. There are some different factors and variables that are considered, but generally speaking, most are going to be in some level of agreement with what we're looking at here. And what we're looking at is the number of liters of dehumidification that are required per cubic meter per day to keep up with your evaporation rate. So in some cases, we don't need as much, just 1 liter per cubic meter per day. In some cases, we need a lot more, up to 3 liters per cubic meter per day. What determines the amount of dehumidification needed is the rate of evaporation from the environment. The more water we have leaving materials, obviously, the more humidity control we need to keep up. And there are some things that determine this. When we try to determine exactly how much is needed, there are really 3 pieces of information you've got to look at. The first piece you've got to look at is just how much air are we trying to control. So what is the volume of that air in cubic meters? The second step is, what is the scope of water? In other words, are you dealing with materials that let go of water rapidly, high evaporation rates? If you're dealing with really high evaporation from something like textiles on the floor as a flooring material, then we're going to need more humidity control than you would if you were dealing with something like a hardwood floor, which lets go of water more slowly. And we put that in sense of small, medium, and large. Dealing with very dense materials to let go of water slowly and or a very small area wet. We're dealing with whole areas that are wet, and we've got some highly porous materials. We put that in the medium category. Or we're dealing literally with the floor, the walls, the ceiling, 3-dimensionally, all of the surfaces within the space, and we call that a large. The next thing we have to decide is what type of dehumidifier we're going to use. If we're using a standard refrigerant, a good example from Dry Ease and Legend brands would be something like the 1200 dehumidifier. Then we need to overcompensate for that technology because it's not the best technology available in industry today. If we're using low humidity refrigerants, then that's a better, more efficient technology. And then we have an entirely separate consideration down here for desiccants, which are not based on liters per cubic meter. They're based on rates of air exchange per hour. Based on these calculations or these quantifications, we then do the math on the structure that we're handling, that we're drawing. And the example here would be if we were drawing a space that measured 7 meters by 3 meters for the floor and had a height to the ceiling of 2.5 meters, then we would calculate first the volume of air at 52.5 meters. We would then look at this loss and determine what is my scope. And let's say, for example, we had floors only affected, but those floors were a textile, a carpet. Then that would be a medium scope. Then we choose our dehumidifier type. In this case, we've chosen a low humidity refrigerant. Well, a low humidity refrigerant under a medium scope gives me a factor of 2 liters per cubic meter per day. So this is what the math would look like. I take my cubic meters, multiply by the 2 required per cubic meter, and I come up with 105 liters of dehumidification required. We apply that then by understanding the rating on our dehumidifiers. And I've just pulled a page down from the Dry-Ease website here, taking a look at the LGR 7000. This particular dehumidifier, and this is important, at its AHEM water removal rating, pulls 58 liters per day. On this example, we needed 105 liters per day. So one dehumidifier would not be appropriate if we were choosing the 7000. We'd need 2 of them, all right, because remember the number here, 105 liters was our minimum requirement. So a very basic and straightforward way to determine the amount of dehumidification required to begin the project. Now, once that dehumidifier is installed and we begin the drying process, at that point, we're going to monitor the environment using hygrometers, and humidity should be in check. What we want to notice as we move forward is that as the water begins to evaporate into the space, then the humidity in the space, using an analogy of a bucket here in liquid water, as the humidity enters the air in the space, that your dehumidification rate is keeping that humidity in check. The humidity should not be increasing over time. Just like in this analogy where we have a bucket, we have a flow rate of water into the bucket and a flow rate out. If water is flowing in at 1 liter per minute and it's flowing out at 1 liter per minute, then the level in the bucket will stay the same. This is our evaporation rate, air movers blowing across surfaces, and our dehumidification rate. The problem is, though, as you begin the process, these may not be equal. And you may experience that the dehumidification rate is not appropriate. If it's not appropriate and we're not pulling water out fast enough, then what you're going to observe is a very rapid increase in humidity in the environment. Now, you'll always see an increase in humidity when you first get started, but that increase in humidity should never exceed about 60% relative humidity. If it's getting well above 60%, you don't have enough humidity control. Now, cautionary note, most of the time when we make adjustments because we see this high humidity, the knee-jerk reaction of most restoration contractors is, let's just add some more dehumidification. Let's add so much dehumidification that the humidity begins to decrease regardless of the amount of evaporation, which in some cases may be okay, but there could be other issues, which brings us into one of our final discussions here today. When we track humidity over time in the drying environment, and we install air movement, we install dehumidification, we are going to see a humidity spike, the humidity increasing as we begin the project. Again, if you've sized the dehumidifiers appropriately for the scope of the loss, this spike should never exceed 60%. If it's shooting well above 60%, then you need to look further into the reason for the humidity spike. And let me give you the case in point. So let's say we had our humidity increase, spiked all the way up to 90%. So you make an adjustment to your dehumidification, and you double up on the number of dehumidifiers, whatever it is. Consequently, the humidity begins to decrease in the environment. Well, everything looks good. Looks like we made the right choice. Well, may not have. If we look a little bit deeper into the reason why we have the humidity spike, then we have to evaluate both sides of the bucket, so to speak, the reason why we have a high humidity. It could be because there is more evaporation than we anticipated, and it could be because we don't have as much dehumidification as we anticipated. Let's drill one layer deeper. On the excessive evaporation side, let's say the reason why your humidity spiked above 60% is because we did not extract the loss properly. Tell you, I've personally accidentally left the dump valve, the discharge valve, open on my portable flood extractor a couple of times after dumping the extractor, then forgot to close it. Well, you're not going to get a very good extraction when that dump valve is still open, sucking in a bunch of air. If that's, for example, the reason why your extraction was poor, adding a dehumidifier doesn't fix that. Um, Adding a dehumidifier is simply going to cover up the symptom that you have a whole bunch of excess water that still needs to be extracted. You're still going to get a lot of damage, extremely poor drying rates. Things are going to remain wet for an excessive amount of time. Let's say that the reason why you had a really high humidity in the structure is because there was an entirely undiscovered wet area. You didn't really find the edge of your migration and find unaffected materials around your entire perimeter. So there's an entire space that's holding on to a bunch of water that hasn't even been addressed, and it's evaporating high volumes of water. Let's say the reason why you have really high humidity is because it's August, and in August we've had a system come through, and it's warm and extremely humid outside, and I've got a bunch of moisture infiltrating from outside because there's a bunch of windows open in the building. Or because there's an air conditioning system or an air handling system that's bringing in 20% of its air from outside as a fresh air recovery. That, again, is not appropriately addressed by adding a dehumidifier. It's addressed by eliminating the infiltrating moisture from outside. It would be a far more efficient way to manage that. Let's say that the reason we have really high humidity is because the water source has not been stopped, or there were multiple sources. Say we had a really hard winter and it's in December. Some high winds along with freezing temperatures have caused a bunch of frozen pipes in a facility or a building. And we did find the broken pipe, fixed the broken pipe, turned the water back on, began the drying process, and lo and behold, the pipe was broken in 4 places, not 1. Adding a dehumidifier does not fix that, right? So these are lots of causes of having a substantial humidity spike where adding a dehumidifier does nothing but cover up the symptom. It doesn't actually address the problem. And this is only halfway through the conversation. Let's go to the other side here. If in adding dehumidifiers you did your math wrong, then sure, we need to increase dehumidification. So recheck your math. Again, calculate for the cubic meters of air in the space. Reevaluate your scope. And is it really a small or a medium, or should it be a large based on what you're seeing? Once you reevaluate the math, sure, if it's off, then let's add some dehumidification. Maybe it's a mechanical problem with the dehumidifier, though. Maybe you installed enough, but that dehumidifier isn't giving you the 58 liters per day that it's supposed to, because the filter looks like it's got 3 or 4 inches of dust on it. So we're not getting enough air through the dehumidifier. If you remove the filter, you should see a nice, bright metal aluminum coil. And if it isn't a nice, bright, shiny aluminum coil, and it's more of a tinged yellow or brownish color, then we're not going to get the water removal from that machine. It needs to be properly cleaned. In addition to that, what if the dehumidifier is not operating properly because you installed the dehumidifier, you got the dehumidifier up and running, but then the homeowner decided that the dehumidifier was a little too loud, so they just turned the dehumidifier off. Doesn't matter if you add another dehumidifier, all you're doing is giving them another power button to push when you walk away. So adding a dehumidifier again here would not be the appropriate fix. What if we've overloaded a circuit? Add another dehumidifier, and I guarantee you will even further overload that circuit. So these are all issues, again, where adding the dehumidifier is not necessarily the appropriate fix. The reason we spend time on this is because it's critical as a restorer, regardless of the circumstance, that we truly define and understand the problem before we ever apply a solution. And the solution is only appropriate when it's based on that true core problem. We must identify that true core problem. So with that said, that's our general summary. Let me walk away from the general summary and throw at you just a few conclusion statements from the first 4 modules of our webinars. Conclusion number 1, if I was to pull out the most impactful information here for you from what we've learned for the last 4 months, the most direct impact on the speed of drying initially is air movement. You must validate that you have a high velocity of flow over every square inch of wet material. Verify this with a hygrometer. If you wanted to overnight have the most dramatic impact on your ability to rapidly dry a building, that's the one thing you'd start doing. As you put your air movement in, walk around with a hygrometer and verify that everywhere you go and every surface you place it against, you're getting the same temperature and humidity. If you're not getting the same temperature and humidity, add more air movement until you get the same temperature and humidity. Use the general strategy we discussed for placement. Use your centrifugal air movers with side inlets at doorways to force exchanges between rooms, and use air movers that are better suited for covering high amounts of surface area like your axial types to address the center of rooms. This one change by itself, I promise to you, is going to have a dramatic impact on your speed of drawing. It's also one of the easiest to implement. Second conclusion, heat and humidity are most impactful on the later stages of drawing. It's also the easier time to deploy them, which is part of what we'll get into in the advanced discussions. But when we need to focus on energy and we need to focus on lower humidities is when we start identifying the areas with slower drying rates. What you'll notice is much of the building is going to respond very well to just the high velocity of airflow. But as soon as we see that response, it's going to start literally making visible the problem areas that are drying at a slower rate. And that's where we're going to focus that energy in that lower humidity. And finally, the third conclusion from our discussion, monitoring is a critical part of what we do. There are a number of unforeseen variables that will influence virtually every project that you process. And the only way we can compensate for those unforeseen variables is coming back frequently to validate that our expectations are being realized, and where they're not, making the appropriate adjustments to shore up against those variables. So with that, that's our summary for the first 4 modules. As we move into the next series, I'd encourage you to take a look at the dryease.uk website. There is a link there for RSA that will take you into the webinars. For the first 4 modules, if you click on the link under those first 4 modules, you'll be able to review, if you'd like, over the next 4 weeks, the information that we covered in those modules, or listen to this module again. In addition to that, starting in November, on November 6th, we're going to go into the first advanced module, drying problem areas. And again, that's going to be November 6th. From there, we'll move in December 4th, the following month, into the next advanced module, documentation quality performance, documenting rather quality performance. So please, I invite you to stick with us as we move through these series. If you'd like any questions, comments, or follow-up on the discussion we had today, feel free to reach out to our UK office, and we'd love to hear from you and get in touch with you on anything specifically that we can follow up with you on. So thank you very much. I appreciate it. Thank you for joining Restoration Sciences Academy and Dryease Products, and we'll talk to you on November 6th.